Good day, everyone. This is Louis Daphne Orense and my partner is Mary Joyce Pantas. And in this video, we'll have our expository paper presented. The title of this expository paper will be Unfolding Optimal Polygons from Square. So this expository paper, entitled Unfolding Optimal Polygons from Square, focuses on two distinct methods on constructing regular polygons. Two methods of which are introduced are using Euclidean constructions and pure origami constructions. Euclidean construction is performed with the help of only two tools, which are the straight edge and the compass, while the pure origami construction are performed with the act of folding. The generalizations on creating n-gons, or the polygons, were presented later on. This study is also proven to be beneficial not only to the researchers, but also to the institution, to the teachers, to the math enthusiasts, and to the future researchers. It will help them gain knowledge on how to use an art in a different way. Artists can create arts mathematically and mathematicians can do math artistically. Also, these future researchers may be the artist who wants to discover more polygons using origamis. In this presentation, we will provide valid solutions and answers for the problems stated below. First is what is pure origami? Second, what are Euclidean constructions? Third is how are these two methods related to each other? Fourth, how are the polygons created using both methods, pure origami and Euclidean constructions? And the last will be how is the optimal polygon constructed from a square? For the list of notations, a capital letter R for the radius of circumscribed circle, a small letter r for the radius of inscribed circle or the apothegm, small letter n for the number of edges or vertices of the polygon, capital letter L for the diameter of the regular n-gon, L sub n for the lines, P sub n for the points, B sub n for the bisectors, A of theta for the minimum stripped width, theta optimal for the optimal theta, F sub n for Fermat primes, and lastly, alpha, beta, delta, and gamma for the angles. This is the part where we answer the questions mentioned earlier. The first question will be, what is pure origami? Pure origami is a kind of origami which is done when geometrical shapes were produced out of a square paper and it does not involve any form of cutting. Just that simple, and some axioms mathematically describe foldings in a paper. Hosida Hattori axioms include creating a line by folding 2 points together, making a fold such that the 2 points meet, creating another fold where 2 lines coincide with each other, creating perpendicular lines, which is also a form of intersecting lines, and lastly, folding the combinations of the previous folds. Based on studies, some classical problems in constructions were discovered in geometry, like trisecting an angle and doubling the cube. These two are proven to be unsolvable using Euclidean constructions, but are proven to be possible using the pure origami. The next question to be answered will be, what is Euclidean construction? These constructions were done using only compass and straight edge. A construction in geometry means to draw geometric objects such as lines, points, circles, and its combinations. Its combinations include intersecting lines, perpendicular lines, parallel lines, angle bisectors, midpoints, and bisectors of line segments. Fermat numbers help determine constructible polygons. Polygons with vertices that are Fermat numbers are considered constructible. Fermat numbers were denoted by f sub n equal to 2 raised to p multiplied by Fermat primes, where p is an element of integer. Fermat primes are denoted by f, which is equal to 2 raised to m plus 1, where m is an integer. In geometry, a constructible number refers to a constructible length. A length is said to be constructible only if it can be represented by any application of compass and straight edge. An example of this is the square root of 2. Square root of 2 is a constructible number since it can be represented as the hypotenuse of a 45-45 90 triangle. The next will be the relationship between pure origami and the Euclidean construction. Listed below are the similarities and differences of the two constructions. A regular polygon can be drawn in Euclidean construction by using two instruments only, which are the compass and the straight edge. In pure origami, it is a process of folding which creates creases. Compass and straight edge construction does not involve any computation since a straight edge is an unmarked ruler, same as the compass. In pure origami, it involves computation since there are angles determined. As we all know in pure origami constructions, it produces straight line, points, creases, while in Euclidean constructions, circles, arcs, segments, and points can be produced. There are also some classical problems in geometry, like an angle trisection, doubling the cube, which are proven to be possible in pure origami and impossible in Euclidean construction. The constructions of regular polygons using the two methods, Euclidean and pure origami, require specific theorems and calculations. Geometric constructions are quite interesting since every point that is constructible using a compass and straight edge is constructible using pure origami. To answer the question on how are we going to construct polygons using both methods, we are going to construct a regular pentagon and a regular hexagon using pure origami, and the regular hexagon using Euclidean construct. To construct a regular pentagon using pure origami, the first step will be fold the square paper to half, creating a mid-crease. Referring to the figure, we need to fold the diagonal of the bottom rectangle, which is AD, and bisect the angle BAD to create AC. We let C touch DG at F, where one endpoint of the newly created crease is B, and note that the angle FPG will be equal. The fourth step will be bisecting the angle FPG with BH, where an angle HBA will be produced, and it is equal to pi over 10. Next will be bisecting the angle HBA with BI, and then the angle IBA will be produced, which is equal to pi over 20. We then fold the diagonal BE. The eighth step will be folding BJ in half, creating KL, which is one edge of the stellated polygon. The last step will be creating a pentagram and then follows the pentagon. Next will be the steps on how to create a hexagon using pure origami. The first step will be to divide the paper vertically and fold both diagonals, BD and AC. Next, we let B touch XY at B', creating the line EA. Third, we'll turn over the paper and fold D onto EA at F and bisect DF with GH and then fold. The fourth step will be letting H touch BD at I to create GJ. The fifth step will be to connect GI and HI to create a triangle. Construct a hexagram from the triangle GHI using symmetries, and this will lead to the construction of the regular hexagon. After the examples presented, we can conclude that constructing a polygon using pure origami requires to generate a stellated polygon before coming up with a regular polygon. The folds lead to an edge of the stellated polygon. With a rotating angle, the stellated polygon is made, and from the stellated polygon, a regular polygon can be constructed. Now, using Euclidean construction, we are going to present how to construct a regular hexagon. The first step is to create a circle with center C. Keep the compass span and place P anywhere on the circle to act as the starting point. Then, without changing the span of the compass, we will place the compass point on P and create a small arc crossing the circumference of the circle. Label it as Q. With the same span of compass, move the compass point to Q and make another small arc on the circumference of the circle and call it R. Keep repeating this process of stepping around the circle until you return to point P. Label the produced vertices as S, P, and U. These 6 vertices will make up the regular hexagon. Based on the example, Euclidean constructions of polygon also include circles, lines, points, and combination of these geometric objects. The last question to answer is how is the optimal polygon constructed from a square? We note that the square had been folded to arrive at a certain edge, which will be the edge of the stellated version of the polygon. Stellated versions of each polygon had twice the number of the vertices than that of the regular polygon of n vertices. Stellated versions are concave, while the regular polygons are convex. The outer vertices made up the regular polygons, and the optimal polygon's vertices must touch all edges of the square, and that one diagonal of the square must serve as an axis of symmetry for the created polygon. So, to conclude, pure origami does not include cutting and can be used to construct polygons by folding. These folds are based on Hozita-Hattori axioms, and trisecting an angle and doubling the cube are proven to be possible using this method. Next, Euclidean constructions create polygons using geometric objects and are particularly based on Euclid's first three axioms. These constructions, being constructed years ago, has many limitations, like trisecting an angle, doubling the cube, and squaring the circles, which are proven to be impossible. Pure origami and Euclidean constructions can both be developed further to have more outputs, simple or complex. They may have limitations and differences, but they are both uninterestingly academic artworks. Also, regular polygons of different vertices was folded in different ways in various number of steps using pure origami and Euclidean constructions depending on their number of vertices, odd and even vertices. And last, the optimal polygon created in this exposition is the regular decagon. In view of the conclusions presented, it is therefore recommended that the future researchers try to discover how to fold the optimal polygon of n greater than 10 vertices inside a square, still with no cutting involved. Another recommendation will be finding the solution to a fifth-order polynomial equation, which is yet to come, that is, the trigonometric functions of 2 pi over 11 are roots to the said polynomial. So thank you everyone for watching this video until the end, and I hope that you've learned something from our exposition. Again, I am Louie Daphne Orense and my partner is Mary Joyce Pantas. Thank you!